Hi, everybody. Excuse me. Okay, so here we are, ready to start the second semester of physical science. And remember, we've done chemistry so far. That is has been our first half of the year. Physical science, remember, is chemistry and physics. So we are going to start in on our physics topics. And we're going to start with motion. Mechanics is the study of motion, kind of the big general view. And we're this chapter 11, are going to focus on kinematics, which is how things move. How fast are they going? What direction are they going? Those kinds of things. And motion's a big deal. Why and how things move has been a topic for a long, long time. Your book goes into some history, and they point out the fact that a lot of this study of motion started with people studying the stars, studying kind of the world around them, but the stars in particular. Remember, um, you know, traveling from place to place, back when we didn't really know where we were going. We didn't have Google. We didn't have, our Maps app to tell us what to do. People had to rely on different markers in the world. And one of the biggest things was to look up at the sky and watch the movement of the stars. And this was really great. And different people, especially people who were sailing, who were traveling by ship, used the stars to navigate. They didn't have any landmarks, and that was good because a lot of the stars' movements were very predictable. So you could follow the star and kind of know which direction you were heading. But while they were charting these stars, like on that, they noticed that some of these stars were moving randomly. And these random movers we now know are the planets. And FYI, the word planet comes from kind of a Greek word for wanderer. But anyway, so that was kind of the start of this study of motion. It's kind of like, what in the heck are these planets doing? And so that's kind of where the chapter is going. Okay. All right, sorry, I'm struggling to get my slide to move here. What's going on? Okay, so here we go. So slide 2. I'm having technical difficulties today, if you can't tell. Anyway, so first we'll start with historically the Greeks, because remember they had something to say about everything. So they just kind of thought about it, and they Aristotle and some of the different philosophers from his time determined that objects move in certain ways because of what they were, because of their nature, kind of because that's what they wanted to do, or that's what they did. And so they said some objects would move downward, like move towards the ground, because that was in their nature. Water flows downhill. Some objects move upward because it is their nature to go up into the sky, air, fire. They said stars, or the things up in the sky, they move in a circular orbit because that is their nature. And the wanderers, the planets, remember, they were unexplained. We didn't really know what we were doing there. So that was the beginning. Not a lot of science going on, but that was the first thought. Okay, so then we had some science. Tycho Brahe and Johannes Kepler, in the 16th century, they were two men who studied the planet's movements. Brahe kept very, very accurate records of the planet's positions, along with the stars, over years, like talking years here. And so he had a very, very good idea of where things were going, kind of, what was happening. And Kepler used those records, used this data, all these data points that Brahe had recorded, and he was a mathematician, so of course he applied math to it, and he came up with some formulas for determining what the planets were doing, and he used it to explain what I don't know if they just used this word then, but it was kind of a retrograde, kind of a backwards, instead of just a circular. They would see some planets that did kind of this kind of loop in the middle, and he eventually determined that the planets were moving in kind of an elliptical shape instead of just a circle. It's kind of more of a flattened circle. And he also used his information to write the 3 laws of planetary motion. So, science, first kind of step. Okay, so then of course we have to mention Galileo. He wasn't so interested in planets necessarily, or he doesn't get a lot of um, uh, credit for planet stuff, but he did do a lot of actual experiments. One of the first people to actually kind of try and prove things scientifically, involving moving objects, particularly falling objects. And he said that objects are going to fall at the same rate if they are in a vacuum, so if there's no air resistance, which is kind of remarkable because he had no opportunity to be somewhere where there was not air resistance. No, no real knowledge of any like a vacuum or anything like that. He also talked about how the shape, the aerodynamics, of course he didn't use that word, of different objects will help them fall. He did supposedly a very famous experiment of, letting 2 different size, like orbs or balls fall from the top of the Leaning Tower of Pisa. So anyway, super amazing the work that he did. This little video is just kind of an intro to that. But one thing to note about Galileo and a lot of the other people at the time who were doing experiments, they didn't have even the most basic of technologies. They didn't have clocks, and they figured this stuff out. So it's really pretty cool. Okay, so then we get to what they call the classic mechanics, and this is someone who should be kind of familiar to you. This is Isaac Newton. Isaac Newton developed the 3 laws of motion, which we'll talk about, and the law of universal gravitation, kind of why planets are pulled towards other planets or why we're orbiting the sun. Did a lot of math to explain how and why things move. He was a brilliant man, and this picture kind of makes me laugh. I don't know why I stuck it on here, but notice he did all kinds of things. You have, the telescope there, where obviously he's looking at the different planets. He's the prism. He was well known for that. The apple falling from the tree, the whole gravity thing. Anyway, just kind of the basics for really this chapter and a lot of the physics that we're going to talk about in the next few chapters. Okay, so hopefully this is kind of in the right order. Sorry, I'm struggling today. Okay, so anyway, so now modern motion models. We've touched briefly on quantum mechanics because we talked a little bit about that with atoms and kind of figuring out where the electrons were. Quantum mechanics, though, describes where very small objects are, or their movement. So things like electrons. Relativistic mechanics, which Albert Einstein worked on, explains the movement of high-speed objects, again like electrons, but other things. Technically, these 2 fields, quantum mechanics and the relativistic mechanics, are the best models, the best explanations for motion, but mathematically they are extremely difficult for most people to understand. And so that picture on there is, who knows what they're really talking about. But so it is the best. We tend to stick with Newton's laws because they're very good explanations. Newton's laws are for what most objects are doing as far as motion goes. And although there is math, it's not like the hard math. So it's kind of good. Okay, so now frames of reference, just kind of some points to make as far as actual studying motion. Motion is studied from a certain viewpoint, and that's your frame of reference. So in your book uses the example of, okay, so right now, watching this video, or, when we talk about this in class, stop and think, okay, are you moving? So you're most likely sitting in your chair, so you wouldn't, again, depending on your frame of reference, think necessarily that you're moving, but you have to remember that, if I was standing on the moon, looking at you somehow, then I would be able to see from my frame of reference the fact that the Earth is spinning on its axis, the fact that the Earth is also orbiting the sun, Also, the fact that the sun is moving within the Milky Way and the Milky Way is actually moving. And so, you're just sitting in science class, but technically you are moving a great distance all the time. And so that's kind of your frame of reference, just kind of something to be aware of. Frame of reference can also affect how you extinguish speeds. How close you are to an object in motion typically helps you determine, or it affects how fast it seems to be moving to you. So, for example, if you were standing downtown, like at the top of the Price Tower, and you're watching cars drive, from that distance, from where you are up there, they look, like they're cars. They don't look very fast. But if you were standing right on the curb and a car went by you at 30 miles an hour, it would feel much faster. And so that's just kind of something to be aware of. Okay, so a couple other things about frame of reference. We will use in our examples kind of coming up number lines. And so these number lines you're familiar with from math. This is a coordinate plane, obviously, on the screen. So just in reference, so this red point in relation to a blue point, what's the, kind of where are we looking at it from? And then the other thing to be aware of is that you are studying a system. And systems are basically the one part that is being studied. And so, the example again from the book is a really good one. It talks about like if you're watching a basketball game, if you're studying motion, there are lots of different things that you could be studying. And so if you choose to study the motion of the ball, whether it's being dribbled or passed, or, someone's making a shot, the spin on the ball, the bounce, the whatever it is, if that's what you're studying, then the ball is the system. Okay, so now moving on, I know we're flying through this. Distance and displacement. They are two terms that we'll use a lot. Distance describes how far an object is from a location or how far apart two objects are. So how close are you sitting to your neighbor, or how far is it, to the bathroom, or, whatever it is. Displacement is how far apart objects are and in what direction. And so, from the science room, the gym is 67 feet north. I made that up, who knows? But, and so displacement, we typically kind of think of it more of like kind of as the crow flies, or, it's a straight line. And so that's what that picture is showing. So that green dotted line, so if you're going from start to finish, is a straight line, that's displacement. But in the real world, like if you're driving somewhere, so like from your house to the school, you might have to curve around to get over here, but you could also look at it from the displacement, a straight line. And if distance and displacement or if distance is in a straight line, then it can be the same as displacement, but typically there's some difference there. Okay, so now this is a number line, obviously. I've gotten some of these examples out of the book, and so we'll talk more about this in class. But if you'll kind of look over this, notice that first off, the distances are just a distance. It's just, for example, that first one is the distance from A to B is 30 meters. For displacement, it will always have a direction. It will tell you which way it's going. So from A to B, you are going 30 meters to the east. And then as you go through some of the different changes, or from A to B to C, notice kind of what is happening and notice the difference. And like I said, we'll go through it. You have a lot of experience with this from math, from when you were really pretty young. So this hopefully will be, once you get over the fact that we're doing math and science, pretty straightforward. There's also a formula that we will use for displacement if needed. So if you don't have a number line, and that is, here's the formula right here in the middle. If I can get my technology to work, I may not be able to. Nope. Oh, well, I'm going to highlight it. Okay. And so you can use this formula, the final location minus the initial or the starting location. And so, just do a very simple subtraction problem. So there's that. And by the way, when we do this test, we'll write down formulas. We'll have a note card. You'll have formulas. We'll talk about units, all that kind of stuff. So Don't be too nervous about the math. Okay, so then what if you're moving in 2 dimensions? What if you're not just going in a straight line? You'll do some extra stuff. And here's some more math, so don't freak out. But we will also be using this, which you should recognize. Here's the Pythagorean theorem. So that's serious math, but you can use it along with some geometric kind of figures, in this case, this right triangle, to figure out distance and displacement. But again, this is these are pretty straightforward math problems. Okay, here's an example. Like I said, we will do these in class together, but feel free to look in your book. They walk through it and give you some of the kind of the steps. Okay, so then kind of the end of the first half of chapter 11, they talk about scalars and vectors, just kind of as words to know. A scalar is any quantity that is just the size or the magnitude of the measurement. So if I said, 35 meters, that's scalar. Or if I said the temperature is 12 degrees, I'm just telling you what it is. Vectors are any quantity that describe with that size, and they give you a direction. So if I said it's 35 meters north, I'm giving you a vector. If I tell you the temperature is 12 degrees and dropping, like I tell you which direction it is going, up or down, that is a vector. Okay, so now moving on, actually describing motion, we are going to talk some more about speed, which we mentioned originally. So speed is the distance that is traveled, the distance traveled in a certain amount of time. And so, so you would have like, miles per hour, that is a speed. And so that's a formula that we will use. There's an example. Again, I happen to know that you have done problems like this since you were like, 4th or 5th grade. So don't get nervous. We're going to do some math. Okay, velocity is the rate at which an object changes positions. So this one basically is the same as speed, except it uses displacement. And so you do have a little bit different wording, but the same basic thing. Whatever the displacement is divided by the time. All right, so here's another example, which we will again work in class. This one is, you have to kind of rearrange it a little bit. Okay, so now what about velocities? Like your book just calls this adding velocities. So it has this little kind of insert page. How does wind affect the plane? And so you want to think about how, that top one, if they're moving in the same direction, which is this guy, so it's moving with the wind. And what happens if you have a plane that's moving directly against the wind? How does that affect velocity? This is a really interesting page. I think if you have any sort of mind for like aerodynamics, or why is it harder to run if I'm running into the wind, or why does it take me longer, or that kind of thing. If you're older and you're worried about gas prices, what's my gas mileage going to be if I have to drive straight into the wind for 4 hours, or something like that. So this is actually something, these are very real world applications, just maybe not something you've thought about in these terms. So here's another one. So what if we have wind not either with or directly against us, but what if we have it kind of coming from an opposite direction? You'll have to use the Pythagorean theorem on this one again. So we will we'll talk about that one. But again, please feel free to work ahead on these and just kind of try and figure it out as you go. All right, so now the book does cover some graphing. There's enough in this chapter, in my opinion, to not worry about that. As far as notes go, we may go back and pick it up in a lab. We'll just kind of have to see on that. But now another description that sometimes is applied with motion is momentum. Excuse me. And this is a property that a moving system has that is based on its velocity multiplied by its mass. And just one thing to note, momentum is considered or is conserved within a system. So if you think about like bumper cars, within that circle, within that, rink, I guess you would call it, every time you hit something, you lose momentum and it gains, but there's never lost, and it goes on and hits something else. And so within that system, you maintain or conserve your momentum. Anyway, momentum is another formula that we will use. It is the mass of the object times its velocity. And there's a little example right there, kind of interesting to compare the momentum of different vehicles. And so based on their velocity and mass. And again, this isn't kind of another real world thing. Football players, you might have kind of experienced this, like if you were lined up against somebody who's way bigger than you, but way slower. He's not going to have much of a velocity, or something like that. So these are, again, kind of things to kind of think about and apply to what you have experienced. Okay, so then what about changing motion? So the big one on this to know is acceleration. And acceleration is a change in velocity in a given amount of time. And so the formula is velocity over time. One thing to note, and we'll talk about it as we work through the problems, the units for acceleration are meters per second squared. And that has to do with the math. And just the way that the units work out together. This is a problem that is kind of more real world, like because things accelerate or decelerate or those kinds of problems. And so there's an example again for you to work out and look at. Oh, another example. All right, and then two more things just to kind of talk about before we get into chapter 12 with the next one. First one is free fall. So we talked about Galileo earlier, and he said that that all objects fall at the same rate if there's no air resistance. So that's the definition of free fall. So free fall doesn't actually happen anywhere on the Earth because of air. It does happen in a vacuum. It happens on the moon. That if you watched that video, you saw that. And so this free fall is it has been calculated to where we know the rate that an object is accelerating at as it is falling on Earth. Different planets have different gravitational pulls, and so the Earth's rate is 9.81 meters per second squared. Different planets will have different gravitational constants. But what this is saying is that as an object is falling, whether it is a penny or a bowling ball or whatever it is, every second that it falls, it accelerates by 9.81 meters per second. So the first second, that's how fast it falls. The second, that's hard to say. It's going to be something like 19.6 meters per second, and this you just continually are getting faster and faster. And so that's one of the complications that you could deal with if you are engineering or developing airplanes, or you're trying to figure out, okay, I'm going to jump out of this airplane. When do I need to pull my chute? Or, how fast am I falling? And so anyway, again, for us, it's kind of like, does this even matter? Yeah, it does. And so, so Galileo, kind of cool guy. Okay, and then last thing, I know I rushed through this, but we will again, go over it a lot more in class. Two-dimensional motion. So we've got circular motion. So if you're moving, obviously, in a circle along a circular path, you always are feeling acceleration because you are constantly changing direction. Remember, straight line, no change. But any little curve, you are changing by however much. So you are accelerating. This is known as centripetal acceleration. And so this is a force that kind of tends to kind of pull you in. This is what causes planets to orbit around the sun, is this centripetal acceleration. And so kind of one of those, you experience this like if you're driving in a car and you take a corner too fast and you feel that pull. And then the other one is projectile motion. Goodness gracious. And this is the motion of a flying object as it is influenced by outside forces. Gravity's a good one. So like throwing a football. If I need to throw it, 20 yards down the field or whatever it is, how high up, like what arc do I need to put on it? How's gravity going to pull this down? I can't just throw it straight because gravity will pull it down more quickly. And so those are, again, not things that you necessarily, if you're out there throwing a football, stop and think, but there is math behind it. There are ways to calculate it. And so that's that projectile motion, and just that the path can be determined. That is called the trajectory. Like if you're firing a missile at somebody, you need to know, okay, how high up, how do I shoot this thing? And so anyway, so there's lots of real world application in this chapter. Physics is not my strong suit. We'll find that out together probably as we go through this. But I think that it has such amazing real world applications that we don't really even think about, that we rely on from day to day. But I hope you find this interesting, that as you go through it, you see kind of how it is affecting you. Okay, talk to you later. Bye.